The last video we focused on what we called the common log, and that common log had a base of 10. In this video we're going to be focusing on what we call the natural log. The natural log is a log function that has a base of e. E is an irrational number, and I've got that written here for you, 2.71828, and then of course because it's irrational it continues on forever. And this E number we call the natural base. E is very useful in growth and decay problems, specifically when you're dealing with continuous growth. So anytime you see a problem about growth or decay and it talks about something being continuous, there's probably going to be E in your equation somewhere. So to show you what the exponential growth, continuous exponential growth looks like, I've gone ahead and graphed this here for you. So this equation in red is the equation of y equals e to the x. Remember, e is just a number, and notice that it starts off really low, it gets really close to 0, and then it continues to rise up continuously up to infinity. The blue line, on the other hand, is our log function, or our natural log, and those equations are written right here down at the bottom. So remember, exponential functions and log functions are inverses of each other, and that means that they are reflected over this line y equals x. That's something we talked about in the last chapter. And so the red and blue line are related. The red is the exponential function with base e. The blue line is the log function with base e. And the way we write that is log base e of x. The other way you would see that, the more common way you'd see it, is the ln of x. So these two equations right here are exactly the same. They're just written two different ways. Okay, so notice they have very similar properties. They have similar trends. They're just reflected over that line. Okay, so y equals e to the x and log base e of x are inverses of each other. And the way we will typically write this is the ln of x. So if you ever see that ln of x, that just means log base e. Okay, so same thing. Make sure you know what that ln means. Now we're going to practice writing the ln, or natural log, in multiple forms. This first example says write e to the x equals 6 in log form. You're going to treat it exactly like we did when we started with the log functions, but by first finding your base. So our base is e, so we're going to write log base e of 6, and remember the exponent goes after the equal sign. Okay, so log base e of 6 equals x. Of course, because we have it as a base of e, that natural log, the easiest way to write this then is to change that log base e to an ln. So most of the time you're going to see ln of 6 equals x, and then we would be finished. So two different ways of writing it, but they are equivalent. So one is not better than the other, but obviously ln is much shorter to write than log base e. Okay, so either way works. Just make sure you know that they're both the same. In this example too, it says write the ln of x equals 2.1438 in exponential form. So now we're going backwards. To do this, I would go ahead and write in your log form with the base of e. So log base e of x equals 2.1438. The reason I changed it from ln to log is just so you can make sure you know what your base is. So here the base is e, so we're going to have e to the power of 2.1438. and then equal it to x. So now we went from having log form to exponential form. And all of these you can type in your calculator. There is an E button as well as an ln button, so make sure you know where those are and make sure you know how to use them on your calculator. And if you're not sure, make sure you ask me in class and I will gladly go through that with you. Now, this condense example, again, very similar to what we've seen with the other log functions. The same rules apply. So when we are condensing, remember any numbers in front become exponents. So this is going to be the ln of 10 to the power of 3 minus the ln of 8. I can go ahead and simplify that by writing the ln of 1000 minus the ln of 8. And then I can use subtraction to now make a division problem. So remember, we're going to divide, and that's going to get us ln of 1000 divided by 8, which is the same thing as the ln of 125. So we went from having 2 natural logs down to 1 using our properties of logs that we learned in the last section. So if you have any questions about how to condense or expand, let me know, but it would also be good to review that previous video to review those properties. We're going to go ahead and jump into some examples where you're going to use those natural logs to solve functions. The first example says solve 4 times e to the negative 2x minus 5 equals 3. You're going to solve this just like you would any other function, and that's to get the x portion of this problem on its own. So to do that, we're going to go ahead and add 5 to both sides. And when we do that, we get 4e to the negative 2x is equal to 8. Then I'm going to go ahead and divide by 4 on both sides. And that's going to get us e to the negative 2x equals 2. And now we have to look at what we have here. We have an exponential function, so we want to go ahead and change this to the log function. And to do that, we're going to have to take the log or the ln of both sides. So I'm going to take the ln of e to the negative 2x equals the ln of 2. Notice I've taken the ln on both sides, and what that does is on the left side it allows me to cancel out basically my base and leave me with my exponent. So these cancel and I'm left with negative 2x equals the ln of 2. And then last step is to divide by negative 2, and that's going to get me x is equal to ln of 2 divided by negative 2, which if you go to your calculator, you should have an ln button. You can type that in and then divide it by negative 2 at the end, and you're going to get that x is equal to negative 0.35. And we're done. Okay, so ln's cancel out e's because they are inverses of each other. Just make sure you take the ln of both sides. Okay, let's try example 2 here. It says solve 5 times the ln of 6x equals 8. So again, try to get the ln portion on its own. So we're going to divide both sides by 5, and that's going to get us the ln of 6x equals 8/5. Now, we can't take the ln of both sides because there's already an ln in our problem, but what we do know is that e and ln cancel each other out. So what I'm going to do here is I'm actually going to take e to both sides, and that's going to cancel out my ln on the left and leave me with 6x equals e to the power of 8/5, because e always has to have an exponent. So e to the first, e to the second, e to some fraction, okay? And so now we can go ahead and type this on our calculator. So we'd get 6x equals, when you type in the e button, you're going to have to type in the fraction in the exponent, and that's going to get you 4.95, and then we can go ahead and divide by 6, and we get that x is equal to 0.83 if you round to the nearest hundredth. And we're done. All right, so the one thing you can remember about natural logs and e's is that they cancel each other out. So if you have an e in your function, like in the first example, you're going to take the log of both sides. If you have the log in your function, you're going to take the e to both sides. Okay, and if you have any questions on those steps or how to type those in your calculator, again, please let me know. And also don't forget to check your solutions after you solve. In terms of application, e is very useful when you're talking about continuous growth or continuous decay. And one of the most common places you would see this continuous growth is when we're talking about compound interest. This formula here that I've got written, A equals P times e to the RT, or PERT, as some people remember it. This formula is used if you have continuously compounded interest. And I'm just going to basically go through an example to show you how it works. So it says, when Larry was born, his grandparents deposited $3,000 into a college savings account that paid 4% interest compounded continuously. So notice here that he wasn't earning a certain amount per year because the interest was constantly being compounded. So that's very important that if you're going to use this formula, it has to say that it's compounded continuously. So the one thing you have to know when you're using this formula is where to plug in your numbers. P in this case is the starting amount. R is your rate. And then of course T is time. And A is your final amount. So when I look at this problem here, I want to go ahead and identify all the parts that I'm given and then plug them in where we can. So when we read this problem, the first number they give us is 3,000, and that's our p-value, or our starting amount. The other number they give us is the 4%, that's your rate. And then here it says, what will the balance be after 10 years? So that's our time. So what we're looking for is our final amount after 10 years. And so all I have to do in this case is just plug in my numbers and then go to my calculator. And that would look like this. A is equal to 3,000 times e to the 0.04 times 10. And remember, rate always needs to be converted into a decimal, so that's very important. And now just go to your calculator, type this in, so you'll have 3,000 times e to the 0.04 times 10. Make sure that the 0.04 and the 10 are both in your exponent for e. And when you solve, you get $4,475.47. That would be in this person's savings account after 10 years. Okay, and that's assuming you didn't take anything out, you didn't add anything extra, you just put $3,000 in and you left it alone for 10 years. All right, if you have any questions about where the E button is or how to type that in, let me know, but hopefully that was pretty easy. The second part to this is if you are given an amount and you want to know how long it would take to get there. So in the same problem, let's assume nothing changes except for the amount we're trying to reach. So this time, the $10,000 is the A value, and what we don't know is how long it's going to take. So this is one where we're going to be working backwards. If I plug in my numbers here, I'd have 10,000 equals the 3,000 we deposited times e to the 0.04 t, because again, we don't know how long it will take. So to solve this, remember in the last slide we said we want to get e on its own, so I'm going to divide both sides by 3,000. When I divide by 3,000, I'm going to cancel out these zeros. It's the easiest way to reduce right away, and that's going to leave me with 10/3 equals e to the 0.04 t. Now I want to get the e eliminated from my equation so that t is on its own, and to do that, remember we said we take the ln of both sides. So I'm going to take the ln of 10/3 and the ln of e, because the ln and e will cancel, and I'll be left with the ln of 10/3 equals 0.04 t. And the last step would be divide by 0.04. So if I divide by 0.04 on both sides, when I type this into my calculator, I believe you get 30.1. And so what that means is that in order to get $10,000 in this college savings account, it would take 30 years at that rate. So 30 years, or just over 30 years. All right. If you have any questions about the solving process, again, let me know. But these exponential growth and decay functions, when they're compounded continuously, they're very good with application. The natural base E is very useful anytime you're talking about growth or decay for continuous rates. You can use it when you're dating fossils. They use it, and scientists use it to calculate the amounts of a substance that would be left over thousands of years. You might also see this in half-life problems. I think in a previous section I gave it a half-life example, but very good application for scientists and researchers. You can use E to calculate population growth. So anytime, just make sure you look for that word continuous, and that probably means you're going to have E in your function. Okay, so if you have any questions about when you would use E, let me know. Make sure you know how to change from log form to exponential form, and that you know the difference between common logs and natural logs. And if you have any questions, just make sure you ask me in class. Thanks for listening.